We begin our journey into Galois theory by recalling the definition of a field. A field F is a set with distinguished elements 0 and 1, binary operations of addition x plus y and multiplication x times y. A unary operation minus x and inversion operation x inverse defined for non-zero elements of f, such that f with a zero element addition and unary minus is an additive commutative group, then f star, which is f without the zero element, with multiplication and inversion, is a multiplicative commutative group. And we have the relation between these two operations is the distributive law. So this means that for all x, y, and z in the field, x times y plus z is equal to x times y plus x times z. Examples of fields are rational numbers, real numbers, complex numbers, and zp, where p is a prime. Let us give an example of a field extension. Consider the following set. So q of square root of 2. So this is the set a plus b times square root of 2, where a and b are rational numbers. There are obvious operations of addition and multiplication on this set, but it turns out that this set is actually a field because here we can do inverses of non-zero elements. And this inversion is done via so-called rationalization. So here, if we take this fraction 1 over a plus square root of 2b, then we multiply numerator and denominator by the conjugate expression. So we have a minus b times square root of 2, and in the denominator we get a plus b square root of 2 times a minus b square root of 2. And by well-known formula, we get a minus b square root of 2 over a squared minus 2b squared. And then this becomes again an expression of this form, because now the denominator is rational. So we have a over a squared minus 2b squared minus b over a squared minus 2b squared times square root of 2. And we point out that since root of 2 is not a rational number, so this implies that that this denominator a squared minus 2b squared is not equal to 0 for pairs AB that are different from a zero pair. So this field is viewed as an extension of the field of rational numbers. In a similar way, the field of complex numbers is written as A plus BI, where A and B are real numbers. And this can be viewed as an extension of the field of real numbers. And we have our basic definition. A field E is an extension of a field F if E contains F as a subfield. And notation that we're going to use in this context, if we write that F is inside E, then here we mean that E is a field extension of F. And an important observation is that if E is an extension of F, then E may be viewed as a vector space over F. Here we see that C is a two-dimensional vector space over real numbers, and the basis is formed by elements 1 and I. Similarly, we can see that Q with a joint square root of 2 is a two-dimensional vector space over the field of rational numbers with basis 1 and square root of 2. The fact that E is a vector space over its subfield F follows trivially from the axioms. So we compare the axioms of the field and the axioms of the vector space, and we see that these axioms completely align. In E, we have addition operation, so this becomes addition of vectors in this vector space. And also in E, we have operation of multiplication of two elements of E. However, here we forget that we can multiply two arbitrary elements of E, and just remember that we can multiply elements of E by elements of F. This will be multiplication by scalars in this vector space. This observation is very important because we can use the tools of linear algebra like dimensions and bases. Definition. We say that extension F to E is finite or respectively infinite if E is finite dimensional or respectively infinite dimensional as a vector space over F. As an example, C is a finite extension of R, and R is an infinite extension of Q. Definition. Let E be an extension of F, and an element alpha in E is called algebraic over F if there exist elements an minus 1, a1, a0 in F, not all equal to 0, such that an alpha to the power n plus an minus 1 alpha to the n minus 1 plus a1 alpha plus a0 is equal to 0. Equivalently, this says that the set 1 alpha, alpha squared, alpha cubed, and so on, the set of powers of alpha, is linearly dependent over F. And we see that without loss of generality, we may assume that an is equal to 1. We can always choose a non-zero leading coefficient and then normalize this expression by dividing by the leading coefficient. We have the following simple lemma that says that if the extension E of the field F is finite, then any alpha in E is algebraic over F. And proof: let n be the dimension of the field E as a vector space over F. So then if we take the set 1 alpha, alpha squared up to alpha to the power n, so this set contains n plus 1 elements, and thus it will be linearly dependent over F. Let alpha in E be algebraic over F. Definition: a monic polynomial P in f of x of the lowest possible degree such that P of alpha is equal to 0 is called the minimal polynomial of alpha. Lemma that minimal polynomial of alpha is unique. And we give the proof by contradiction. So if P and Q are both minimal polynomials of alpha of degree n, so that is the monic, and the P of alpha and Q of alpha are both equal to 0. Then f of x, which is P of x minus Q of x, is a polynomial of a lower degree such that f of alpha is equal to 0. If P is different from Q, then f is a non-zero polynomial, and we can normalize it to make it monic. And so this will give us a contradiction, because by definition, p and q were polynomial of the lowest possible degree, such that alpha is a root. Our next lemma says that the minimal polynomial p in f of x of alpha in E is irreducible in f of x. And proof, again by contradiction, so if we can factor p of x as r of x times s of x, where degrees of r and s are lower than degree of p, then if we substitute alpha in this equality, we get p of alpha, which is 0, is equal to r of alpha times s of alpha. And from here we get that either r of alpha is equal to 0 or s of alpha is equal to 0, since the field cannot have divisors of 0. And this gives us a contradiction, because by definition of the minimal polynomial, p was a polynomial of the lowest possible degree that has alpha as a root, and degrees of r and s are lower than the degree of p. So this motivates our notation for minimal polynomial is irreducible alpha f. Right? So this is our p of x. It will be the irreducible polynomial with coefficients in f that has alpha as a root. And an exercise is that there exists a unique irreducible polynomial in f of x that has alpha as a root, and this will be the minimal polynomial of alpha. As examples, we see that the minimal polynomial of a square root of 2 over the field of rational numbers is x squared minus 2. This polynomial is a monic irreducible polynomial in q of x, and it has square root of 2 as its root. And irreducible polynomial or minimal polynomial of I over the field of real numbers is x squared plus 1. Again, this polynomial is irreducible in R of x and has I as a root. We have the following definition. An extension E of the field F is called algebraic if every element alpha in E is algebraic over F. And what we saw that if E is a finite extension, then it is algebraic. But the converse is not true. We could have algebraic extensions which are infinite. We will use the following notations. Let E be an extension of F. Then this symbol will stand for the dimension of E as a vector space over F. And so this could be a finite number or infinite. We will call this the degree of an extension. And here is our first theorem. Suppose we have a double extension. So F is an extension of K and E is an extension of F. Then the degree of E over K is equal to the product of the degree of E over F times the degree of F over K. Let's give a proof. Let the set xi be a basis of F over K, and let yj's be a basis of E as a vector space over F. Then our claim is that the set of pairwise products xi, yj is a basis of E over K. To prove that something is a basis, we need to establish two properties. The spanning property, that this set spans E as a vector space over K, and we need to establish linear independence over K. First, so let alpha be an element in E. Since yj's form a basis of E over a field F, then we can write alpha as a linear combination of yj's with coefficients cj's in the field F. And we also have that xi's form a basis of F over K. So this means that each cj can be written as a sum over I of dij times xi, where dij's belong to K. Combining this, we get that alpha is the sum over ij of dij xi yj, with dij being elements of K, and from here we conclude that the set xi yj spans E over K. Now, secondly, we need to prove linear independence. Suppose a linear combination, so sum over ij dij xi yj is equal to 0, with dij's in K. So we need to show that for all I and j, dij are equal to 0. Let us set cj to be the sum over I dij times xi. Since xi's are elements of F, so these are also elements of F. And then we have that the sum over j cj yj is equal to 0. But the set of yj's is linearly independent over F. And from here we conclude that for all j, cj must be equal to 0. So this tells us that for all j, the sum over I dij xi is equal to 0, because this is our element cj's. But the elements xi are linearly independent over K. And this tells us that for all I and j, dij must be equal to 0. And what we get is that the set of xi yj is linearly independent over k. And now we conclude that the set of these products is a basis of E over k, and since the dimension of a vector space is the number of vectors in its bases, and we have this multiplicative relation between these three different bases, so we conclude the desired equality. Suppose we have a field extension and alpha is an element of E. We will distinguish between the following two objects. So f of alpha will be a subring in E generated by alpha. So f of alpha is the set of all polynomial expressions an alpha to the power n plus a1 alpha plus a0, where aj's are elements of f, and n is arbitrary. And we consider f in round brackets alpha. So this is a subfield generated by alpha. So here, this object consists of all possible fractions, so g of alpha over h of alpha, where g and h are polynomial expressions, so g and h belong to f of x, with the condition that denominator is not equal to 0. We can see that these expressions will form a ring. We can add them and multiply them, and the rational expressions will form a subfield. Here, not only we can add and multiply such expressions, but we also can take inverses of non-zero elements of this form. What we want to show is that if alpha is algebraic over f, then actually these two sets are the same. The field extension with alpha is equal to the ring extension with alpha. And for non-algebraic elements, this certainly will not be true. Let us prove the following proposition. Let P be a monic irreducible polynomial in f of x. So we can write p of x as x to the power n plus a n minus 1 x to the n minus 1 plus a1x plus a0. So then our claim that the quotient of f of x by the ideal generated by p of x is a field. Now let us try to understand better the structure of this quotient. This polynomial may be viewed as a reduction rule. So we can write that x to the power n is equal to minus a n minus 1 x to the n minus 1 minus a1x minus a0 in the quotient. Simply because p of x is equal to 0 in the quotient. So by equating this polynomial to 0 and moving the tail to the right-hand side, we obtain this relation in the quotient. From here, we see that the set 1x x squared up to x to the n minus 1, so this is a basis of the quotient over the field f. And in particular, the degree of this extension is equal to n, the degree of the polynomial p. To prove that this is a field, we need to show that any non-zero element of this quotient is invertible. Let's give a proof of this fact. Let G be a linear combination bn minus 1 x to the n minus 1 plus b1x plus b0 be non-zero, meaning that some of these coefficients are non-zero. or because this is a basis, so this will be a non-zero element in the quotient. Consider the greatest common divisor of p of x and g of x in the ring of polynomials. We know that in the ring of polynomials we have a Euclidean algorithm, and thus we can compute the greatest common divisors. Since p is irreducible and g is not divisible by p, we conclude that this greatest common divisor of p and g must be equal to 1. And then, from the extended Euclidean algorithm, we conclude that there exist polynomials u and v in f of x such that this greatest common divisor, that is 1, is equal to p of x times u of x plus g of x times v of x. Then, taking this equality mod p, we conclude that v is equal to g inverse in the quotient f of x, quotient by the ideal of p. So this proves that every non-zero element in the quotient has an inverse, and thus this quotient is a field. Consider a ring homomorphism. From f of x to f of alpha. Let's call it pi. So which is the evaluation homomorphism. So here pi of some polynomial f is equal to f evaluated at alpha. It's easy to see that this evaluation map is a homomorphism of rings. Now let alpha be algebraic over f, and let p be its minimal polynomial. Then it's easy to see that the kernel of this homomorphism is precisely the ideal generated by p. Well, certainly, since p of alpha is equal to 0, p is in the kernel of this homomorphism, and using the argument of division with the remainder, we can see that this kernel consists of exactly multiples of a polynomial p. The map pi is surjective, and then by first homomorphism theorem, we conclude that the ring f of alpha is isomorphic to the quotient ring f of x, quotient by ideal generated by p. But what we proved that this is a field, and it follows that every non-zero element h of alpha in f of alpha has an inverse. In f of alpha. And this tells us that this ring extension is the same as the field extension with alpha. And so we conclude that this ring extension is a field and thus coincides with the field extension with alpha. And as a corollary, we get that if alpha is algebraic over f, then the degree of the extension of f of alpha over f is equal to the degree of the irreducible polynomial of alpha over f. In a similar fashion, we can define finitely generated extension. So here we have, suppose E is an extension of f, and let alpha 1 through alpha k be elements of E. So then we set the field F with elements alpha 1 through alpha k as the set of G of alpha 1 through alpha k over H of alpha 1 through alpha k, where G and H belong to the ring of polynomials in k variables, and the denominator, so H of alpha 1 alpha k, is not equal to 0. So clearly the subset in E of all such expressions will form a subfield. And a subfield in E is called finitely generated over F if it has this structure. Another corollary is that if alpha 1 through alpha k are all algebraic over F, then F of alpha 1 alpha k is a finite extension of F. And proof by induction on K. So the basis of induction is established in this corollary, and the step of induction is that alpha j plus 1 is algebraic over a field fj, which is F with the joint alpha 1 up to alpha j. Since alpha j plus 1 is algebraic over F, it is also algebraic over fj. And then, by our multiplicativity theorem, we conclude that the composite of finite extensions is finite. We conclude this lecture with the following proposition. Let E be an algebraic extension of F. And suppose alpha is algebraic over E. That is, it sits in some larger field and is algebraic over E. Then alpha is algebraic over F. So here we have a chain of extensions. So F sits in E and E sits in E of alpha. Now it's tempting to use the dimension argument and say that the degree of extension of E of alpha over F is equal to the product of E of alpha over E times E over F. And since alpha is algebraic, the degree of E of alpha over E is finite. But the problem is that this could be infinite. So here we only say that it's algebraic and we don't say that it is finite. So if that extension were finite, then we would immediately get the result. But we could possibly have infinite algebraic extensions, and so this argument does not work. Or at least it does not work directly, so we need to modify it a little bit. Now let's give a proof. Let P be the minimal polynomial of alpha over E. P of x is equal to x to the power n plus an x to the n minus 1 plus a1x plus a0, where all aj's are elements of E. Consider the field F with the joined elements an minus 1, an minus 2, a1, a0. So this will be a subfield in E. Since every element of E is algebraic over F, by this corollary, f of an minus 1, a1, a0 is a finite extension of F. But now we can apply our dimension argument. So what we have is we have a tower of extensions. So we have this extension, f with the joint coefficients of this polynomial. And then we can adjoin alpha to this field. The point is that alpha is algebraic over this intermediate field. Since its minimal polynomial has coefficients precisely in this field. And then we get that this extension is finite by corollary, and this extension is finite because alpha is algebraic over this intermediate field. And then, so this tells us that this extension of f of an minus 1, a0 with alpha over f has a finite degree, and every element of a finite extension is algebraic over f. From here it follows that alpha is algebraic over f. And this completes the proof of this proposition.